Hi guys, this video is going to talk about the third free response. Actually, it's numbered number 3 on the pendulums. So this is one of those problems where they don't give you any numbers really. They're telling you the mass is m and the length is L. But if we draw a free body diagram, the first question is a free body diagram. Like before, we want to make sure we're careful with the free body diagram. One thing is on this test, even if it was an in-person test, you could use a ruler. You should use a ruler. And so if you are doing this by hand, you ought to use a ruler to do it by hand. Make your lines straight so that it is neat, it's easy to grade. But the other thing is, like I was talking about on the last problem, you need to make the lengths accurate or somewhat accurate. So for instance, this is all you should have here. You should not have anything else. I'm going to put a couple of additional lines in there, but then I'm going to erase them. So one thing is this force of tension, the y component of it needs to be equal to the F sub g, right? And then this x component needs to be equal to this vector, the applied force. So when you draw this F sub t, it needs to be at a 60-degree angle, and it needs to be about the length where this would be one leg and this would be the other leg, and that is the hypotenuse. So just keep that in mind as you are drawing your free body diagrams. Use a ruler and try to be as accurate as possible and only have the basic information. You do not put components in there. You only put the vectors. Okay, so that's going to be our free body diagram. Okay, now, as I was talking about before, the y component of that force of tension is going to equal the gravitational force, right? Those two vectors are canceling each other out because it is sitting there. It is not moving. If it's not moving, everything has to be in equilibrium. And so this vector length is the same as this vector length. So if this is force of gravity, this is force of gravity, which is mass times gravity. So that's what I'm starting off my argument with, is that the force of tension in the y direction is equal to force times gravity, which means that is mass times gravity. The problem does not give us a number for mass, it just gives us m. So I'm done with that for now, but this was not the question. The question was the tension in the core, that is F sub t, not Fty. So now I need to find F sub t. Well, if I look at what's going on, I'm going to go back to my SOHCAHTOA, and I'm going to consider that the cosine of 60 degrees is the adjacent over the hypotenuse. So that is, the cosine of 60 is the adjacent mg over the hypotenuse F sub t. Now at this point, again, we're trying to find the tension in the string. You could do a couple things. I think what I'm going to do is algebraically, we can switch these two, and we can put ft over here and cosine 60 over here. I'm going to do that. Okay, if I go to my calculator and I make sure my calculator is in degrees, because this is in degrees, I'm going to type in cosine of 60 and see what I get. And I get 0.5. Okay, dividing by 0.5 is the same as 2 times. So the force of tension is 2 mg. That's the answer. There's no numbers. Remember, that's it. And if you're still stuck on how I got the 2, dividing by 1/2 is the same thing as multiplying by 2 over 1. And so that 1/2 turns into 2 over 1, and we get a 2 times mg. Okay, this next question is one of those where we're going to have to find that height differential. In other words, I'm going to draw it on here. We're talking about from here and it swings down to here. Well, what is the difference in this height? And we need to find this, because this is an energy problem. Well, it is an energy problem, but what we need to find this height. Because of the energy problem, the energy portion of it would be the gravitational energy is equal to kinetic energy, and that is mg delta y is 1/2 mv squared, and so we need that delta y. Well, how are we going to find it? Well, this is L, and when it comes down here, this is also L. So this length from here to here is L. What we need to know is this piece of it, how much was cut off basically from here to here. Well, let's find this piece and then take that away from the L. okay? And that'll tell us the leftover part. So this piece, go back to our SOHCAHTOA for just a second. Well, this is our 60 degree here. This piece is going to be cosine again. So I'm going to go back. The cosine of 60 degrees is adjacent over hypotenuse. The adjacent's what we're looking for. Let's call that, I don't know, I'm going to call it H again. Let's call that H, and over the hypotenuse, which is L. So this H is, if I multiply both sides by L, well, first of all, cosine of 60 is 0.5, right? Then let me multiply times L. So H is half of L, okay? So if this is half of L, this must be the other half of L. So this piece is 1/2 L, which means that our delta Y is 1/2 L. Okay, let's go back to where we were a second ago. Let's remember that delta Y is 1/2 L. Let's just kind of have that over on the side. You could call it L over 2. That is something that we need to know. I'm going to go back to my energy equation like I was a minute ago. The reason I need to do that is I need to find the velocity because I need to be dealing with centripetal force, and centripetal force is mv squared over r. So I'm going to start off with the energy equation. That is, the potential energy is equal to the kinetic energy, so that is mg delta y is equal to 1/2 mv squared. I'm going to cancel my m's, and I'm going to get the same thing I had on the previous problem. That is, this is going to be a 2g delta y and a square root of that. So v is equal to the square root of 2g delta y. Well, I know what delta y is. It's 1/2 L. So v is equal to the square root of 2g times 1/2 L. Well, this 1/2 and this 2 tell me that the velocity is really just the square root of g times L. Okay, the reason I needed that is I need to go back and talk about tension, but tension depends on centripetal force, and so I had to have the V because centripetal force needs V. Okay, so going back to a concept that we covered a little bit ago, that the net force is a centripetal force. That is what's causing it to move. Because this question is asking us about what happens after it swings. So it's moving, so there is centripetal force. That centripetal force is the net force. Well, what is the net force? The net force is the difference between the tension and the gravity. I can now, because I want to really solve for tension, because they want to say how strong is it, can it support this tension? I'm going to do one more thing. I'm going to move that F sub g to the other side. So the tension is gravity plus the centripetal force. So the tension is the force of gravity, which force of gravity is mass times gravity, and plus the force, the centripetal force, and centripetal force is mv squared over r. All right, I need to start plugging some things in. Anything that I know, I can plug in. Well, mass, we've been told, mass is just mass. So this is just mg, can't change that at all. M, still M. Okay, V, we actually have V, and we need to square it. If I square the square root, I'm going to get rid of the square root, right? So it's just going to be mgl over. The r is the radius, which in this case is actually L. Let me go back just for a second in case you were lost on this. The square root of, if I took, where can I do this? I'm going to do this down here and then I'm going to erase it. If I took the square root of GL and I squared it, that would just give me GL. Okay, that's where this GL is coming from. So I square the square root. Okay, also though, these L's cancel each other out. And so now I have mg plus mg. Well, what's mg plus mg? It's 2mg. And the question was, show that the cord strong enough to support the object before the string is burned is also strong enough to support the object as it passes through the bottom of its swing. Well, before, the tension was Ft, was 2mg. Now it's the same thing. It is 2mg still. So we can make a little note and say that yes, it is strong enough? Okay, you can word that however you want to. I just said, yes, it is strong enough. It has the same amount of tension here as it did at rest. I will say that in the next couple of weeks, we will be working on practicing for the AP test. But one thing the AP test does is they will have you do problems like this where you have to do both calculations and explanations. And so your sentences need to really explain the concept, not just show the work, but then also explain it. Okay, the last question, the motion of the pendulum after the string is born is periodic. Is it also simple harmonic? Why or why not? The answer is no, because the angle is greater than 20 degrees. So if you can look here, you can see it's raised up at an angle of 60 degrees. That will go back and forth, true, but it will not be simple harmonic motion because it is greater than 20 degrees. We didn't really get into why in this class, but it is true that it has to be 20 degrees or less in order for it to be simple harmonic motion.